Hello, let's talk about math again. Today I would like to talk about the Moufang property in polar spaces. First, I will tell you why we are interested in this. Then I would like to define polar spaces. For that, I would like to define what a point-line geometry is first and also what a projective plane is first. Then I would like to explain what the Moufang property for polar spaces means. Then I would like to prove that generalized quadrangles in polar spaces are Moufang. And then I will give a little bit of an outlook how we can use that to show that also the surrounding polar space is Moufang. Okay, why are we interested? So, in group theory, people try to find out more about groups. Turns out that oftentimes it helps to let a group act on a nice geometric space, and then you can find out more about the group. A nice geometric space is, for example, a building. A building is a geometrical object, also a combinatorial object, that sometimes appears in different fields of mathematics. And buildings were introduced originally by Bruhat-Tits in order to study semi-simple algebraic groups. So buildings were a very useful tool to find out more about these groups. And now when you do your research in mathematics and somewhere you can see that there's a building and you want to use that building, work with that building, sometimes it can be very helpful to know whether or not non-trivial automorphisms exist. That means automorphisms that are not just the identity. So, buildings are nice geometrical objects that we want to use, that appear everywhere in mathematics, maybe not everywhere, but in many areas. And we want to use these buildings, but for that sometimes we need non-trivial automorphisms. And now the Moufang property, if a building has the Moufang property, it guarantees you that there are non-trivial automorphisms. So Moufang property means we have a rich automorphism group. So that's why we are so interested in the Moufang property. So now why are we interested in polar spaces? For this whole video it will not be important to know what a building is or understand what a building is. I'm just giving you the historical context, the motivation and where all of this came from. So if you have a building, then there's always a Coxeter group attached to that building. And the spherical buildings are the ones that have a finite Coxeter group attached to them. And the finite Coxeter groups are classified. So we have a list of the Coxeter diagrams. And we know, when we know the Coxeter diagram of a building, we know something about the geometry of a building. And it turns out that, for example, buildings of type AN correspond to projective spaces, buildings of type BN or CN correspond to polar spaces. So that's why polar spaces are interesting, because one reason why they are interesting, because they correspond to buildings. Then you can also, there are more different kinds, not only AN and BN, there are more different Coxeter diagrams and more different buildings. In general, if you have a building, a spherical building, you can have a projective space, a polar space, or a parapolar space. But for this video right now, we are interested in the polar spaces. A famous result by Bruhat-Tits says that all thick irreducible spherical buildings of rank at least 3 have the Moufang property. So that is very strong and very nice, because we are interested in buildings and interested in the Moufang property. The proof is a bit technical, and my PhD advisor, Professor Dr. Linus Kramer here in Münster, thought that it could be nice to maybe find an alternative proof for this theorem and make this proof geometrical, so that one can see what happens. And the idea was to view buildings as projective spaces, as polar spaces, parapolar spaces, and then construct these automorphisms directly and see what happens in these spaces. And that was the main goal of my PhD project. And now, together with Hendrik Van Maldeghem, we looked at the polar space case and tried to construct these automorphisms that we need for the Moufang property. And we did that successfully, and it was really the case that with this geometric proof we were able to see more clearly what happens. We were able to find out about the relationship of elations and projections, and also we could see the fixed point structure a little bit more clearly. So this is how this all happened, and this is why we were interested and what this is all about. So now, in order to tell you what a polar space is, I would like to define point-line geometry first. A point-line geometry is something that consists of a set of points, a set of lines, and a relation that tells us about the relationship of the points and lines. So we have points, we have lines, and something that tells us whether a certain point is on a certain line or not. And then we also want two axioms. We want that every line has at least 2 points, and we want that lines do not repeat. What does that mean? If you have a line, you can have points on that line, and you can also kind of view this line as a set of points. And what we don't want is that in our set of lines, there are 2 lines with the exact same point set. That means that lines should not repeat. So point line geometry, we have points, we have lines, something that tells us whether a certain point is on a certain line or not. Lines have at least 2 points and lines do not repeat. This is the point line geometry. Now a little bit of vocabulary, because I think I can't do without. If we have a point P and a line L, and the point P is on the line L, we say that P and L are incident. If we have 2 points P and A are on a line together, we say that P and A are collinear. If we have 2 points P and A, and there does not exist any line such that P and A are on the line together, then we say P and A are opposite. And if we pick out a point in our space, let's call it P again, and we look at all the points that are on some line with the point P, then this set of points, including P, we call the perp of P. So the perp of P is just all points that are collinear to P. Collinear, we have a line between 2 points. Opposite, we don't have a line. Incident, if the point is on the line, and the perp is just a set of all points that are collinear with a certain point. So a polar space is a special kind of point-line geometries. There are in general different kinds of point-line geometries. But before I talk about what a polar space is, I would like to tell you what a projective plane is. A projective plane is a point-line geometry as well, but we want to add 3 other axioms. First of all, if we have 2 points in our projective planes, we always want that there's a connecting line between these points. There should always exist a connecting line between points. Then the second axiom is any two lines intersect in a point. So all lines intersect. And the third one is there exist 4 points in the plane, at least, for which none 3 are collinear. So what does this last axiom mean? It means that somewhere in this plane there exists a quadrangle. Because if you think about a quadrangle, you have 4 points, and pick out any 3, then they are not on one common line together. So, projective plane, we want connecting lines between all points, all lines intersect, and somewhere there exists a quadrangle. And I will now show you an example. In this example you can see all lines intersect, there are connecting lines between all points, and I will also draw in where you can find one quadrangle. So now what is a polar space? A polar space is a point-line geometry as well, and this time we want to add 4 other axioms. The first one is every line has at least 3 points. The second is no point is collinear to all the others. So there should not exist a point that is on lines with all of the other points. Very important. Third one, if we have a point P and a line L such that P is not on L, then P should be collinear to either exactly one point of the line L or to all points of the line L. This is also called the one or all axiom, and this is the most important one that we will use the most, the one or all axiom. Point, line, such that point is not on line, then either there's some point on the line L such that there's a line between that point and P, but there are no lines between P and any other points of L, or there are lines between P and all points of L. So either one or all. And then the fourth axiom that we want to add, this needs a little bit of explanation that I will also give you. The last axiom is that any chain of singular subspaces or projective subspaces in the polar space is finite. And what does that mean, and where does this come from? So, a projective plane is a projective space of dimension 2. We can also have projective spaces of other dimensions. For example, if you just have a point, that is a projective space of dimension 0, a line is a projective space of dimension 1, and we can also have higher dimensional projective spaces. That will not be relevant for this video because we will mainly focus on the lower dimensions. But yeah, so a projective plane is just an example for a projective space. And now if we are in a polar space, sometimes we can find subspaces in the polar space where all points are collinear. And these subspaces are projective subspaces. And if we are in a polar space, we can always find projective subspaces. For example, if we are in a polar space, we have points, we have lines, we could have projective planes in there as well. And we actually define the rank of a polar space to be one more than the highest dimensional projective space we can find in there. So for example, if we are in a polar space and we can find a projective plane, but no other higher dimensional projective subspace, then the polar space would have rank 3. So just one more than the highest dimensional projective subspace we can find. And now what does it mean that any chain of these projective subspaces should be finite? It means if you have a point and that point is on a line and this line with the point is in a plane and we are in a polar space and we would go on like that, then we would not go on forever. This is what a chain is. We have these projective subspaces that are incident and that increase in dimension, but these chains should always be finite and not go on forever. This is what this last axiom means. Now to one other important word. Let delta now be a polar space of rank n. We will call delta thick if for every n-2 dimensional projective subspace it is contained in at least 3 n-1 dimensional projective subspaces. What does it mean? Let's look at a rank 3 polar space again. It means that a point is on at least 3 lines and a line is in at least 3 planes. This is what thick means. And in the following, we will basically only look at thick polar spaces and focus on rank 3, but also look at rank 2 a little bit. But the rank 2 polar spaces we will look at will be contained in rank 3 polar spaces. But the rank 3 polar spaces, we want them to be thick. So I also have a little picture for a rank 2 polar space. You can see points and lines. We have that every line has 3 points. We have that no point is collinear to all the others. So notice that in the middle we did not draw in a point because we don't want the lines to intersect there. And we also have that if we have a point and a line, such that the point is not on the line, then the point is collinear to actually exactly one point of that line. So either it is on the line or collinear to exactly one point of that line. And now to give you another fun fact, the rank 2 polar spaces are also called generalized quadrangles. How does this all fit together with the names that we give these things? Think of a quadrangle. It is kind of special because if you pick out a point, then you always have that this point is either on a line or collinear to exactly one point of a line that it is not on. But that also means that we can always have an opposite point. Look at a regular quadrangle, then like these 2 points here are opposite. We always find opposites. So maybe that's why it makes sense that polar spaces are called polar spaces, and also that if we think of the essence of a quadrangle, why it is so special, then yeah, maybe it makes sense that the rank 2 polar spaces are generalized quadrangles. And now another fun fact, since opposite things are such a huge thing in our polar spaces, it is very interesting because if you are in a higher dimensional polar space and you look at 2 opposite points and you look at the perp of these 2 opposite points and intersect them, then the intersection defines a generalized quadrangle. And that is very nice, very pretty. And we will use that fact. And now I would like to define another word. Suppose we are in a rank 3 polar space and we pick out a point A. And now we want to define a new point line geometry using this polar space and this point A. So we say we draw a point in the new point line geometry for every line in the old geometry that contains the point A. And we want to draw a line between 2 points in the new geometry if in the old geometry the corresponding lines were contained in a plane together. And the new geometry that we get, this we also call the residue of A. And now what is also very cool, if we look again at the intersection of the perps of 2 opposite points and then we get the generalized quadrangle, we can actually identify the residue of A with the generalized quadrangle in the intersection. Because we have that A is collinear to every point on the quadrangle, and because of the one or all axiom, because we know that every point has to be collinear to at least one point of each line. So this is why this works. And this will also be very useful. Okay, now that we know a little bit about polar spaces, I would like to tell you what the Moufang property is, and it will at first not be understandable because there are some words that will appear that I haven't defined yet, but I want to give you an outlook where we want to go and why I will define the words I will define in the following. So, a polar space has the Moufang property if for each half apartment that we can find in the polar space, the group of automorphisms that fix the inside of the given half apartment pointwise and that stabilize everything that intersects the inside of the half apartment somewhere acts transitively on the set of apartments that contain the given half apartment. So now we have to find out what half apartments are, what the inside of a half apartment is, and what all of this looks like. So I have many pictures for what apartments look like, but first I want to give you the general definition such that you can see the pattern behind it. So let's start with the rank n polar space, and then we want to look at a set of points x1 ... xn, y1 ... yn, such that all the points in the set are collinear except for the pairs xi and yi, for I in the set 1 ... n. So we have a set of points, 2n points, such that all of them are collinear, except the pairs xi and yi. And now an apartment in our rank n polar space consists of all projective subspaces spanned by this set of points. And if you start drawing and think about things, you can actually see very fast that you always get hyperoctahedrons that way. So that's also quite cool. So I told you we are mainly interested in the lower rank polar spaces. So a rank 2 polar space, what do the apartments there look like? These are just regular quadrangles because, you know, we have the set of points is 2n, consists of 2n points. So in the case of a rank 2 polar space, we get 4 points, and such that all the points are collinear except for like pairs, the pairs xi and yi. So that's why we get a regular quadrangle. And for a rank 3 polar space, you know, we need 6 points, and then we get a regular octahedron. And now we still want to know what half apartments are. So let's start with the rank 2 case. There our apartments are the regular quadrangles, and we want to find out about half apartments. So take a regular quadrangle and cut it in half. There are 2 different ways of cutting it in half. And then we want to say that basically the idea is everything that is on the one side of the cut is one half apartment and on the other side is the other half apartment. But you can see, like for example, if we have a quadrangle and we cut it like this, you can see it's a bit difficult because these lines above and below, to which half apartment should they belong? And no, that's why the inside of the half apartment is so interesting, because we want to differentiate between half apartments and also insides of half apartments. So everything that is strictly on one side of the cut should be the inside of the half apartment, and everything that has some intersection with the cutting line there should be also contained in the half apartment, but not on the inside. So in the pictures you can see it quite clearly. I colored in pink the inside of the half apartment, and then in blue what also still belongs to the half apartment but is not in the inside. And that way you can get two half apartments. And then with the other way of cutting it is the same. I colored in pink the inside, and in blue what still belongs to the one half apartment but is not on the inside anymore, and then the other half should be the other half apartment. So this is what it looks like for generalized the apartments and generalized quadrangles. And now with the octahedron we want to do the same thing. We want to cut it in halves, and there are again two different ways of cutting. And now you might think, but why is there not a third way? I could think of a third way of cutting the octahedron. And yes, but the third way of cutting is not allowed. And for that one needs a little bit of background information about buildings. So I can give you a short explanation right now, but it might not be understandable because I don't want to explain everything about buildings in this video. It's not that relevant. So apartments, half apartments are also sometimes called roots. And in general building theory, we know that roots always correspond to foldings and reflections. And now, like heuristically, or like just to give you a picture, if we look at the quadrangle and we look at the different ways of cutting, the orange lines, we could see that the upper half we can reflect along the orange line, and then we get the lower half. And with the octahedron, the two allowed ways of cutting it, we can also see if we take one half and reflect it along the orange, we get the other half. And now with the third way of cutting, this would not be the case. So, because half apartments are roots, and roots always correspond to reflections, that's basically why this third way of cutting, we don't want it. So if you did not understand that explanation, it's fine. There's more behind that. So actually, it is always the case that there are always two kinds of half apartments, because there are always two kinds of roots, long roots and short roots. But this all, it's basically a different topic. So for us right now, let's just accept that the octahedron, we can only cut, only these two ways of cutting are allowed and no other ways. So, and then we can do the same thing. We say that everything that is strictly on the one side of the cut is the inside. Everything that is somewhat incident with where we cut is still in the half apartment but not on the inside. And this is how we obtain the two different kinds of half apartments. And you can see in the pictures what I marked. The pink I marked at the inside, and then the blue again still belongs to the half apartment but it's not in the inside. Okay, let's remember the Moufang property again. Moufang property, a polar space has the Moufang property if for every half apartment the group of automorphism that fix the inside of the half apartment pointways stabilize everything that has some intersection with the inside of the half apartment and acts transitively on the set of apartments containing that given half apartment. So we know what half apartments are, what the insides of half apartments look like. Now we still want to know what the transitivity looks like. And for that I also prepared some pictures. So if we think of the rank 2 case again, our apartments are the regular quadrangles, and the inside of half apartment in the one case is just the one line with 2 points, and then we want to see other apartments that contain that half apartment, but we want some transitivity here, but we know what has to be fixed, so we can see what the transitivity would look like. Also in the second case, the second kind of half apartment, you can also see it very easily, what has to happen. And with the octahedrons I also have 2 pictures. So basically the one time we want to fix the upper half of the octahedron and be able to move the lower point around, and in the other case we want to fix the one side of the octahedron and want to move the other side around. This is what we want. And now to the proof that generalized quadrangles and rank 3 polar spaces are Moufang. So what we have to do is we have to find these automorphisms. We have to look for a half apartment, and then we have to find an automorphism that fixes the inside, fixes everything that is intersecting this inside, and that has the transitivity that moves things around in a certain way. And now remember that in a rank 3 polar space, if we take two opposite points and we look at the intersection of the perps, then this defines a generalized quadrangle. So we can view generalized quadrangles as the intersection of these perps. And that thing we will use now to construct our automorphism. So the plan is all the elements in the generalized quadrangle we can also view as elements of the residue of A. And then instead of thinking of a point in the generalized quadrangle as a point, we think of it as a line between that point and the point A. And then we have a line in the residue of A that corresponds to the point in the generalized quadrangle. And then what we want to do is we want to project from the residue of A to another residue, to another residue, to another residue, and back. And then see that if we compose all these projections, we get the desired automorphism. So now, of course, we have to understand how projections work. And for that, let's look in the octahedron. Let's say we have a point X and we have a point Y, and we want to view the point X as the line AX. And now we want to go into the residue of Y. What do? We project the point Y onto the line AX, and then we get a point, because we know that every point has to be collinear to a point on a line. It can't be the whole line. This has some reasons, then I would have to explain a little bit more about polar spaces, but I don't want to do that right now. Also, I mean, you can just think about it, right? You have the axioms, and it's if you think about it, I'm sure you can figure out why. So you have the point Y and this line, and project Y onto that line, get a point, and then the line that you then get between that point and Y, this will be our new line in the residue of Y. This is how we project from the residue of A to the residue of Y. This is how it works. So I will tell you now about the construction of the automorphism, and then we want to see why this construction works and does what we want it to do. So we have the octahedron, we call the below point A, the above point P, and then we have this one line there that we call B prime and Q prime. And our goal is to find an automorphism that fixes Q prime, B prime pointwise, and then we want to move things. And let's say we have a point T that we want to move to a point S. And now we have to find points in the octahedron such that if we project into the residue of these points, everything works out. So what do? Let's pick a point B on the line AB prime. And then we want to look at the line AS and the line BT. Our goal is later to move T to S. And now let's call the intersection point of AS and BT S prime. And we want to project S prime to the line Q prime P. And then the point that we get there, we will define as the point Q. And what we want to do is, so the automorphism that I want to define now is the automorphism that we want to show is the desired automorphism, will be the projection from the residue of A to the residue of P to the residue of B to the residue of Q and back to the residue of A. So first we want to see why this moves T to S. Okay, we start with the point T. In the residue of A, this is the line AT. Project into the residue of P. Because P is collinear to T, we get the line PT. Then we project into the residue of B, but T and B are also in the same plane together, so again we have a line there, so we get the line BT. Then we want to project into the residue of Q, so we have to project Q onto the line BT, but we know that this is just the point S prime. So we get the point S prime, we get the line QS prime next, and then we want to project back into the residue of A. But S prime is collinear to A, so we get the line AS prime, but the line AS prime is just the same as the line AS. So if we now look at the intersection of AS with the generalized quadrangle, we exactly get the point S. And that is why this automorphism, for the generalized quadrangle, it moves T to S. This is exactly what happens. Now let's look at why the line Q prime B prime is fixed pointwise. Pick any point on that line Q prime B prime. Let's denote it by N. So N is actually in the intersection of the residues of A, P, B and Q. So it is already clear that nothing can happen. We have the point N, and then we start with the line AN, projects to the line PN, projects to the line BN, projects to the line QN, projects to the line AN. Nothing happens, we just stay. So that is why all the points on the line Q prime B prime are fixed pointwise. Okay, and now we still need that all the lines that go through either Q prime or B prime are stabilized. And we do that by looking at the planes through A B prime and the planes through A Q prime and see that they are stabilized. First, let's look at random plane through A B prime, and I just pick a third point C such that I can refer to this plane as the span of A, B prime and C. And we start with that plane, and now we want to project it into the residue of P. So the projection of P onto that plane will be a line through B prime. That it will be a line is again a property that we get out of the polar space axioms that maybe one would have to think about a little bit. But if you can accept it for now, then accept that if we project P onto this plane, we get a line, and since P is collinear to B prime, this line has to go through B prime. And then it intersects AC in some point C prime. If we then project into the residue of B, so we know that B was already in the plane A, B prime, C, because B is on the line A, B prime. And also the projection of P onto that plane is of course in that plane. So B is already collinear to that whole line. So we get the same plane again as we started with, the A, B prime, C. Then we do the same as Q. We project Q onto that plane. We again get a line. But then if we project back to A, we already know, well, we started with the plane, then the line, the projection that we get is in that plane. And so if we go back to the residue of A, it is again the same plane. So that is why the planes through A, B prime are stabilized under this automorphism. So now let's see what happens with the planes through A, Q prime. That is a little bit more complicated, but it's okay. So pick any arbitrary plane through A, Q prime, and again we want to have one third point that we call D, only such that we can refer to this plane as A, Q prime, D. We start with that in the residue of A, and now we want to project into the residue of P. Project P onto the plane A, Q prime, D, and then we get a line through Q prime that intersects the line A, D, and some point D prime. So we now have the plane P, Q prime, D prime. Now we want to project B onto that plane to see what happens then, because next we want to go into the residue of B. And then we get the projection of B onto the plane Q prime, P, D prime is a line through Q prime that intersects B, D prime in some point that we will denote by D prime prime. So now we have the plane B, Q prime, D prime prime. And now what happens when we go to the residue of Q? We know that Q is on the line P, Q prime. So Q is already collinear to Q prime. Also, Q is collinear to D prime prime. Then we can just write the plane Q, Q prime, D prime prime as the plane P, Q prime, D prime prime. But then again, D prime prime is collinear to D prime, so we can just write this plane as the plane Q prime, P, D prime prime. And that is again the plane that we got after the first projection. So if we now project back into the residue of A, we knew exactly where this plane came from. So we get the same plane through A again. And that is why the planes through A, Q prime are also stabilized. So now you can see we did everything that we wanted to do. We had an apartment, we fix the inside of a half apartment pointwise. We know that we fix all the things that intersect the inside of the half apartment. And we know that we have this transitivity, we can move certain points to different points. And this is how it all works out. And now for the Moufang property, you would also have to show that you can find these automorphisms for the different kind of half apartment. So we would have to look at the different kind of half apartment and then again show that we can find an automorphism such that the inside is fixed pointwise, everything that intersects the inside is stabilized, and we have transitivity. One can also do that, but I will not do it in this video. I just wanted to give you an idea what I have been working on. For the other kind of half apartment, we also have something. Actually, there's also a theorem that says that if you show it for one kind of half apartment for a generalized quadrangle, that already implies the full Moufang property. But that is not so important right now. What I want to talk about next is that we can actually extend the automorphism for the generalized quadrangle to the surrounding polar space. So if we look at the apartments in a rank 3 polar space again, the octahedrons, and we also know there are two different kinds of half apartments, but for the one kind of half apartment, we can see the generalized, the quadrangle there does the exact same thing like what we did with the apartments for our generalized quadrangles. And now we already know that we can find these nice automorphisms for the regular quadrangles, for the apartments in the rank 2. And we can use that to construct the automorphisms in the octahedrons. So that should give you an idea, and I have a full proof for that. Yeah, and that's what I've been working on. And actually, with this, I told you that with the geometric proof, you can see a few things more clearly. For example, what is new and what we found out is that all the planes through Q prime B prime get fixed point-wise. That tells us more about the fixed point structure. This we did not require for the Moufang property. We also found out that these automorphisms, we can write them as a composition of projections. So we found out a little bit more about the relation between these automorphisms and projections. And that was also a nice thing. And now if you wanted to know where we want to maybe go with that, there are things called the even group of projectivities and the little projective group. And I think we can, I mean, we already did that. We found some connection and we would like to determine more of these groups. And yes, that's what we are working on. But I will keep you updated. Thank you for watching. I hope it was somewhat understandable. I know it was like only giving a rough idea about what's happening and not giving all the technical details and stuff. Wanted to keep it short this time. Yeah, thank you for your attention. Goodbye.